Quality education is a human right.
Hey guys, today we're going to learn implicit differentiation. To start, we're going to use two examples to illustrate when to use explicit differentiation and implicit differentiation. Okay guys, out of these two equations, the one on the left should look really familiar since you have practiced a lot of problems with David. And the way to differentiate it, or how it's called rather, it is just explicit differentiation, which is just a normal way to differentiate. So we are going to do dy over dx equals, so for the x squared, we're just going to bring down the 2, so it becomes 2x. And for the 3x, the x is removed, so we just turn it into a 3. And for a constant, which is 1 right here, the 1 is a constant, the derivative of a constant is just 0, so we are not going to add anything. And now David has mentioned before that a different way to write dy over dx is just y prime, which will become very important later. And you can see that the difference between these two equations is that y isn't isolated like we have it over here. And also, we have y squared, which will make it different. But to differentiate it, we call it implicit differentiation. So first, let's just find the derivative of both sides. D over dx, d over dx. And now let's start with the 9, since 9 is a constant. The derivative of that is just 0. And for x squared, remember we just turned it into a 2y. But for y squared, we're into a little problem here. Since there are no x's in y squared, we can't really differentiate that. But there's a little cheat that we can do to differentiate that. So firstly, let's just do d over dx squared. Like we've done before, it's just 2x. But for d over dx y squared, we can't really do it like I've mentioned before, is because we don't have any x's in the y squared. So what we're going to do is do d over dy y squared. And it's a little cheap because we aren't really doing what we're asked to do. We were supposed to do d over dx, but we're doing d over dy. And now, to fix this little cheat, what we're going to do is add a dy over dx. Now, theoretically, if we were supposed to multiply this, you would see that the dy's cancel out, leaving us with just d over dx, which is what we wanted to begin with. So, first thing I'm going to do here is write the derivative of y squared with respect to y. It's just like we've done it before with respect to x with x squared. So this just becomes 2y. And like I've mentioned before, dy over dx can be written as y prime, like I said over here on the left. So we are going to add that y prime right there. And that is how you differentiate y squared with d over dx with respect to x. So let's add that. Let's write it 2x plus, we're going to resolve this, and that is 2y prime equals 0. And now lastly, we just need to isolate the y prime. which firstly we're going to do is 2y, we're going to subtract 2x from both sides, which leaves us with 2y prime equals to negative minus 2x. And then we are going to derive both sides by 2y to isolate the y prime, negative 2x over 2y. And now we just need to, now we just need to simplify that. And that is just going to be y prime equals x over, negative x over y. And in the next slide, we are going to show how to solve this x with using explicit differentiation to see the benefits of implicit differentiation. In this slide, we have the same equation twice. And in the last slide, we solved this equation using implicit differentiation, which gave us y prime equals to negative x over y. And now we are going to solve this same equation using explicit differentiation. So the first thing we want to do is isolate the y. So we'll do y squared equals to 9 minus x squared. This is because we needed to move the x squared into the other side so that we can have y squared by itself. And that just means that we have to subtract by both sides minus x squared, which gave us 9 minus x squared. And to isolate just the y, because we just want the y, we don't want the y squared, we're going to have to square root both sides, which will give us plus or minus 9 minus x squared. And now we've run into an issue here because now we're going to have to differentiate two equations, one being positive radical 9 minus x squared and negative radical 9 minus x squared. And so right now, we're just going to focus on the positive one, which is just 9 minus x, radical 9 minus x squared. Now, if you remember what David taught us that it is easier to derive a radical when we have them in a fractional exponent. And so radical 9 minus x squared will become 9 minus x squared to the 1/2. Before we start deriving, we still need to notice that we are going to have to use chain rule here. And so the first thing we want to do is notice the outermost function, which is something to the 1/2. And then the innermost function is 9 minus x squared. So for the 1/2, we are going to do 1/2 9 minus x squared, and we need to do 1/2 minus 1, so that becomes negative 1/2. And now for the innermost function, we are going to just derive normally, which is just 9 is a constant, so that turns into 0, and negative x squared, we just bring that to 2, so negative 2x. And now we just need to simplify. So we'll rewrite this as y prime. And if you remember in pre-calculus, to change that, oh, I forgot a negative here. To change that negative x squared, negative 1/2, we need to flip the 9 minus x squared that's in the numerator into the denominator. And so in the bottom, we will have 9 minus x squared over, to the 1/2. And so, lastly, we need to multiply that 1/2 and this negative 2x. Now you'll realize that when we multiply these two, it becomes negative 2x over 2, which means that we can just get rid of the 2's and multiply 1 times minus x, negative x, which we will put in the numerator up here. And that is how we solve this x squared plus y squared equals 9 with explicit differentiation. And now the question is, did we get the same thing when we did implicit differentiation with explicit differentiation? And so, first, well, we need to identify what the y was. And if you remember that we solved the y right here. We isolated the y from right here. And so that is going to become equals to negative x color negative x over 9 minus x squared to the 1/2, which, if you notice, is the exact same thing that we got when we did it explicitly. Let's review the strengths and weaknesses of implicit differentiation. The strengths is that it is usually much faster, as you can see. Explicit took many steps. And y doesn't need to be isolated like we did in explicit differentiation at the beginning. The weaknesses, though, is that y prime now depends on 2 variables, meaning that if we want to find y prime, we cannot just be given the x like we can when we did explicit differentiation, since all the variables are x. But in implicit differentiation, we will need both the x and the y to find y prime. And so in the next few slides, we will go over examples that require implicit differentiation. In this example, you can see that we have p's instead of y's, which we just used to add variety. But we can also see that we have a p cubed and the p isn't isolated, meaning that this is a great candidate for implicit differentiation. So let's first derive by both sides. And let's start with the right side, since there's x's. So you bring down the 5, multiply by the 3, 15, and subtract 5 by 1, which gives us 4. And so now let's go on with the other side. As you can see, we have our problem again, that we do not have we don't have any x's in 2p cubed. 2p cubed. So we need to do a little cheat where we do d over dp, which is the derivative of 2p cubed with respect to p. And to fix it, we will add, like we did before, dp over dx. We did dy over dx before, but since we have a p here, we are doing dp over dx. And so you will differentiate this one normally. So this will become 6p squared. And like we said that dy over dx is y prime, we will also say that dp over dx is p prime. Let's write that here. So 6p squared and now you notice that if we're deriving a variable with respect to x when it's not x, we always have that variable at the end with the prime. And so whether it be with y prime or p prime, we always have that variable with prime at the end. So we first differentiate normally. So with respect to p prime, so 4p is just 4, but then we add our prime since we are deriving with respect to x. So we got 6p squared p prime plus 4p prime equals to 15x to the 4th. Now we just need to isolate our p prime. And to do that, we'll first factor p prime from 6p squared p prime plus 4p prime. And so that would become 6p squared plus 4 p equals to 15x to the 4th. Now lastly, we must isolate our p prime. So we divide 15 x to the 4th by 6p squared 6p squared plus 4. And that is our answer for p prime. And in the next slide, we will use an example to list out the steps for implicit differentiation. Guys, these are the steps for implicit differentiation. And the first one says, find the derivative of both sides of the equation. So, put derivative there and derivative there. And let's start with the left side. So the 2x just turned into a 2. And the y squared, remember, we first derive it normally, like 2y. But then since we're deriving it with respect to x, we need to add that y prime at the end. So equals to, again, y, we just turned into a 1, but then we need to add that y prime. And we can get rid of that 1 because we don't really need that. And then since 1's a constant, we don't add anything because the derivative of a constant is 0. And so what we're left with is 2 plus 2y prime equals y prime. Now let's look at the second step. Move all the y primes to one side of the equation. So let's move this 2 to that side. making it 2y prime equals to y prime minus, and now we still need to move that one y prime to the other side. So we'll do 2y prime minus y prime, because to move this y prime to the other side, we must subtract both sides, equals to -2. Now factor out the y prime. So to do that, we do y prime 2y minus 1 equals to -2. And lastly, isolate the y prime. Y prime equals to -2 over 2y1 minus 1. 2y minus 1. And in the next slide, we will have you try your first example on your own. All right, let's have you guys try this example on your own. Pause me now and come back when you're ready. All right, let's tackle this question. So the first step says the final derivative of both sides of the equation. So first, let's do e over dx on both sides. Then let's start with 3x squared. So we bring them to the 2 and multiply by 3. So 6. Then we just take 1 from the 2, which is 6x. Now remember, with 5y squared, since we're deriving with respect to dx, we can use our little cheat where we could just find the derivative normally. So 10y, because we bring down the 2, and then we subtract 1 from the 2. So 10y, but we can't forget our y prime. Always have to have a y prime when deriving with respect to x. And then since 88 is a constant, we can just put that the derivative of 88 is just 0. Number 2, move all the y primes to one side. So to do that, we need to move this 6x to the other side. And we can just do that by subtracting both sides by 6x. So that will look like 10y prime equals to -6x. Thirdly, says factor out the y prime, which we do that would look like y prime 10y equals -6x. Then lastly, isolate for y prime. Now that means that we just need to divide 10y by -6x, or -6x divided by 10y, which look like -6x divided by 10y. And that is our y prime. We can simplify this further by simplifying the 6 and the 5, which would make it -3x over 5. And in the next slide, you will also try another example on your own. Okay, Now you guys will try this example on your own, but before that, we'll identify where we have to use chain rule. And so we'll use chain rule for sine of 3x, with sine of 3x being the sine being the outermost function, and 3x being the innermost function. We will also use it for cosine of 7y, where cosine is the outermost function and 7y is the innermost function. Pause me now and come back when you're ready. All right, let's tackle this one. So first it says find the derivative of both sides of the equation. So we will put d over dx on both sides. And first, let's start with cosine, where cosine is the outermost function, so the derivative of cosine is negative sine of 7y. And then we multiply that by the innermost function, the derivative of the innermost function. So remember, we just derive it normally, so that'll be 7, but then we add our y prime. Next, we'll start with 4y to the 4. So we derive it normally, giving us 16 y cubed, and then we add our y prime at the end. Now we do sine, so plus, and now the derivative of sine is cosine, and so we would derive a cosine and then derive the sine and then give us cosine, leave what's inside, then multiply that by the derivative of the innermost function, which is just 3. Okay, now we found the derivative of both sides. Now number 2, move all the y primes to one side of the equation. So first, we could do that by moving the cosine 3x times 3 to the other side, which would give us 16y cubed y prime equals to, now we will move our constants in the front because it just looks better and is more organized and it is easier to work with. So negative 7 sine of 7y prime sine of 7y minus, we will also move the constant in front, 3 cosine of 3x. Okay, now we have our y prime still on this side and we need it to go on the left side. So to do that, we will add 7y prime sine of 7y. So 16y, move that up, 16y cubed y prime equals to, plus 7y prime sine of 7y equals to negative 3 cosine of 3x. Now, factor out the y prime. Let's do that. Just factor it out, and we get 16y cubed plus 7 sine of 7y. And on the other side, we still have negative 3 cosine of 3x. Now lastly, we isolate for y prime. So to do that, we divide both sides by 16y cubed plus 7 sine of 7y to both sides. So that would look like y prime equals to negative 3 cosine of 3x over sine, 16y cubed plus 7 sine of 7y. And now for the next slide, we will talk about second derivatives. Now we will find the second derivative, but for explicit differentiation first. So to do that, we must first find the first derivative, which we know how to do. So for the first derivative of 4x to the fifth, you just bring down the 5 and multiply by the 4, which is 20. And then 5 minus 1, so 20x to the 4. Now, for the second derivative, the notation can be written like this, as d over dx of dy over dx, but it is most commonly shown as the second derivative of y, which is just, we do the same process over. We bring down the 4, so 80x, and then to the third. 4 minus 1, 3. It's 3. Now, another way that we can write the second derivative of y is with primes. And with that, well, we know the first one, so it's just y prime. So you bring down the 6, multiply by the 8, so it's 48x to the fifth. And then for the second derivative, we could also write it as y double prime. And then we do the same process over. Bring down the 5, multiply by 48, which equals 240x to the fourth. We can even do it a third time, which would be y triple prime, which would equal 960x cubed. Now in the next slide, we will talk about the second derivative, but for implicit differentiation. Now we will use implicit differentiation to find the second derivative. Now, if you remember, we found the first derivative of this equation, which was y prime equals to negative 2 over 2y minus 1. And so we just follow the steps again. So we find the derivative of both sides, y double prime equals to, wait, we notice that to derive this, we need to use quotient rule, unless we move the 2y minus 1 up to the numerator, which would look like negative 2 times 2y minus 1 to the power of negative 1. We can do this because it's safe to assume that there is power to the power of 1 when 2y minus 1 is in the denominator. So To move it up, we have to change that the exponent to a negative. And so that helps us out a lot, because then we don't have to do quotient rule. And so we just have to do chain rule. And so let's identify the most outer and inner equations. So the most outer equations are -2, -1, and the most inner equation is 2y minus 1. So let's find the derivative of -2 times 2y minus 1 to -1. So first, we do the outermost equation, which would look like 2, because we bring down the negative, 1 times the -2, which turns it just to 2, times 2y minus 1 to the power of -2, because we subtract 1 from -1. Then we have to do the most inner, After that, we need to do the most inner function, which would look like times 2, because remember that we derive this normally, but then we add our y prime at the end. And then -1 is just a constant, so the derivative of a constant again is 0. So let's organize this. And see y prime equals 2. First we multiply. Let's actually first bring the 2y minus 1 to -2 back to the denominator, because we don't really want a negative exponent, but we made one because we needed to, because it would make it easier. We wouldn't have to use quotient rule. So let's put 2y minus 1 squared. And over that, we still have the 2 and the 2y prime. So when we multiply that, that would look like 4y prime. But wait, we know that we have y prime, so we can simplify this even further. So this would look like 4 over 2y minus 1 squared. And now we just need to find where our y prime was. And so remember at the beginning, we started that our y prime was, or is, -2 over 2y minus 1. And so what we do is we multiply 4 over 2y minus 1 times 2 over 2y minus 1. And so when we multiply this, we get 8 over since we have 2y minus 1 squared, and then another times 2y minus 1, that will make it 2y minus 1 cubed. And that is our y double prime in terms of just y. Now, differences is that with implicit differentiation, we always want to plug in back our y prime so that we can just have our answer just in y's. And in the next slide, we will use or see a word problem using implicit differentiation. In this problem, we are asked to find the tangent line of a curve when x is negative 1/2 and our y value is the positive. So as David has showed us that when we want to find a tangent line, we need both our slope and our point. Now, first, since we don't have our point because we are missing the y value, we need to find our point first to find our slope. So what we have right now is negative 1/2 y. And so to find it, we are going to plug negative 1/2 into this equation. So that will look like 2 times negative 1/2 plus y squared equals 2 y plus 1. Now we can simplify this, the 2 and the negative 1/2, and that would be negative 1. But I am going to move everything to one side, and you'll see why in a bit. So negative 1 plus y squared, then we subtract minus y, and then the minus 1 as well, minus 1, which the other side will equal 0. Then let's combine like terms. So y squared minus y, then minus 2, because negative 1 minus 1 is negative 2, equals 0. Now you can see that we have a quadratic function here. And to find our values, we just need a factor. And so that's why I moved everything to one side, because we are going to get a quadratic and we need to factor. So first we need to find of two values that add up to negative 1 but multiply to negative 2. So those two values are negative 2 and 1. Negative 2 and 1. And so our two factors are y minus 2 times y minus 1. No, plus 1. And so when we make y minus 2 equal to 0, we get 2. And then we make y plus 1 equals 0, we get negative 1. And we have two values, but we are told that our y value, is a positive value. So we will get rid of our negative value, and we will use y equals 2. Now we have our point, which is negative 1/2, 2. Now we can find our slope. Now to find our slope, we will need our first derivative, which, if you remember, we found. It's y prime equals to negative 2 over 2y minus 1. Now, sometimes you will need both the y and the x, because we are going to plug in this point into this function to get our slope. But since we have no x's, we will not plug in our x. We will only plug in our y. So y prime when, remember this notation, means when y is equal to 2. So we plug it in, and we get y prime equals to 2 over, oh wait, sorry, negative 2 over 2 times 2 minus 1 and see, we just simplify. So we get 2 times 2 is 4, minus 1 is 3. So negative 2 over 3. And that is our slope. Now, lastly, to find our tangent line, we need to set up our equation. Y minus y1 equals to m times x minus x1. So our y minus 2 is equal to our slope. So negative 2 over 3 times x minus, well, plus, because since we're minusing twice, because negative 1, because there's a negative 1/2, this is plus, so plus 1/2. And that is our tangent line. In the next video, you will see David find the derivatives of both logarithmic and exponential functions.
If you have any questions or any practice problems you would like to understand better, please comment them down below. During our bi-weekly Q&A, we will tackle these problems from the comment section.
Please like and subscribe so that our videos can reach more calculus students. See you next time, you sleuths.